All right, let's get started. So welcome everybody. Today we have Dr. David Kring, who's a principal scientist at the LPI. He's been with LPI since 2006. Dr. Kring received his BS with honors in geology from Indiana University and PhD in earth and planetary sciences from Harvard University. His research interests are extensive. He explores the origin and evolution of the solar nebula, geologically active planetary systems, Earth, Moon, Mars, and several smaller planetary bodies. His research also includes impact cratering on Earth and its effects on Earth's environment. He has extensive experience as a field geologist. Today, he's going to talk about the Chicxulub impact event and its effects on the on the Earth, on the microbial system. So please take it away. Thank you.
Thank you very much. Yeah, so this is a nice shot that Chris Lowry at UT Austin captured of the drilling rig that we used to capture the latest core from the Chicxulub crater, which is just off the north coast of the Yucatan Peninsula in Mexico. Oh, nice. Laptop has frozen. Just give me a moment.
Okay.
There we go. Okay, so this was a major expedition. It was funded by the International Ocean Discovery Program and the International Continental Scientific Drilling Program. And so any type of effort like this, it's a team effort. And so I have listed here all of the names of the people who helped recover core on the drilling platform, or helped log the core in Germany, or helped with some of the specific analyses that I'll be describing today. The results I'll be talking about today are reported in 3 published papers. One of them in Science Advances about 6 months ago. And then Sarah Simpson, as part of her thesis studies, published a paper in ESL. We have a paper in this month's Astrobiology, and those science results are captured in a popular science article in this month's issue of Astronomy and Medicine as well. So you can get more details of what I'll be talking about in those papers if you would like. Okay, the first thing I have to do is introduce the Chicxulub impact crater. And to introduce the Chicxulub impact crater, I have to begin with the Cretaceous Tertiary, or KT boundary. And this is a picture of what that boundary looks like in the geologic record in Colorado. And so the bottom portion of the screen that you see here are a series of Cretaceous sediments. These are rich with fossil remnants of dinosaurs, dinosaur tracks, and the relics of the ecosystem in which they lived. The top half of this picture are the first tertiary sediments. They had a single dinosaur fossil. I mean, the biota of the world dramatically changed between the top and between the bottom and the top of this picture. Not only did dinosaurs disappear, but 75% of the species on Earth disappear at the same time. And that time is marked and indicated by that white clay-rich unit that you see going through the center of the diagram. So geologists wondered for nearly a century what happened at that interval in the geologic record. Well, a really important piece of evidence was extracted geochemically by Luis Alvarez and some colleagues in California.
Dr. Kring, I'm sorry to interrupt. Your audio is breaking up, and it's breaking up for everybody. So would you please stop sharing your video to see if that improves your presentation?
Testing, 1, 2, 3, 4, 5.
I think it's better. I'll let you know.
Okay.
Yeah, sounds better.
Okay. Luis Alvarez and colleagues analyzed the element iridium in these sediments. Iridium is a really interesting element. It's a siderophile element, which means it likes to go with iron. And the cosmic abundance that accreted to Earth ended up in the core and the mantle. So there's very little iridium in the crust of the Earth. So in fact, when they analyzed Cretaceous rocks, which you see in the lower part of the diagram, it's essentially zero iridium. When they analyzed tertiary sediments, which is in the top of the diagram, again, they got effectively zero amount of iridium. But right in the boundary claystone, they had this tremendous anomaly of iridium. And they interpret this to mean that there was a tremendous amount of additional meteoritic material added to the Earth at that point in time. And in fact, they calculated that that amount of iridium would be produced if a 10-kilometer diameter asteroid hit the Earth at that moment. And they then went on to suggest that that impact event so severely altered the environment of the Earth that it drove dinosaurs and most life to extinction. Okay, so their work begged the question, where is the impact site? And it took about a decade for the scientific community to locate it. Again, a key piece of evidence is shown here in this slide. This is on the island of Hispaniola. This is in Haiti, near the village of Balak. In the lower left-hand corner, we have Cretaceous sediments. In the upper right corner, we have tertiary sediments. And in between, we have nearly a ½ meter of impact ejecta. Okay, and you might say, well, how do you know it's impact ejecta? Well, it is composed in large part of these impact melt spherules. They're glassy to altered impact melt spherules, ranging in size from about 1 millimeter in diameter to a full centimeter in size. In addition, that unit contains abundant shock quartz. So here's a single crystal of quartz, and you can see that there's these striations going across it. Those are what we used to call shock lamella, we now call planar deformation features. These are essentially microcrystalline faults through the quartz crystal where the quartz structure has been converted to glass. And you can see that there's two orientations visible on this particular view, but if you rotated this grain, you would see additional sets of planar deformation features. So it was clear that that unit was in fact an impact ejected unit. Now, the thickness of that unit was important. As I said, it's about a ½ meter thick, whereas other deposits, like that first deposit I showed you in Colorado, are 1 centimeter or less in scale. That indicated to us that the impact site was very close to where the sediments in Haiti were deposited. That led us to look for circular features in the Gulf of Mexico and region, or the Proto-Caribbean region, and that led us to a buried geophysical anomaly on the Yucatan Peninsula. Here is the gravity signature of that geophysical anomaly. The gravity ranges from about -16 to +36 milligauss. And this type of anomaly attracted Pemex, the oil exploration company of Mexico, because these types of anomalies oftentimes are traps for petroleum. They drilled 3 exploration holes. C1 is Chicxulub 1, S1 is Sucapac 1, and Y6 is Yucatan 6, and they all came up dry. No significant petroleum, and so they walked away from this. Geologists did look at the material that the boreholes encountered, and Lopez Ramos interpreted the geophysical anomaly to be the product of a buried volcanic province. Now, knowing that impact structures are oftentimes mistakenly identified as volcanic units initially, we requested samples from one of those boreholes, and we were given 2 thumb-sized fragments from about 1.2 and 1.3 kilometers beneath the surface in the Yucatan 6 hole. And I made 2 thin sections from those 2 samples, and you see them pictured here. The first sample was a polymic breccia. It contained fragments of impact melt within it. Within the impact melt and within the matrix of that breccia were crystals of shocked quartz, one of which you can see there on the right. The second unit, the deeper unit, was a melt rock with a very unusual composition. It did not lie on any magmatic liquid lines of descent. It had a completely unique composition. It's the type of composition that one would produce if you bulk melted the crust of the Earth down to a depth of about 29 kilometers. Within that melt also were entrained relic fragments of the target rocks, and those relic fragments also contained chalked quartz. And so we had evidence that there was an impact crater here on the Yucatan Peninsula. So the geophysical anomalies on the Yucatan Peninsula were created by an impact crater, which we also showed to be the source of KT boundary debris. So, and we call that crater Chicxulub. Now that was a very brief introduction to Chicxulub and how it was discovered. By the time we located the impact site, hundreds of papers had been published by investigators from around the world. So if you want more details about that work, send me an email and I'm happy to recommend about a half dozen review articles. Okay, so moving on. Another important point before I leave those two samples to make is, although they had evidence of shock metamorphism and indicated that structure was an impact crater, those shock metamorphic features were overprinted by hydrothermal alteration. The impact glass was altered to clay. Voids within both units were filled with secondary calcite and anhydrite, and there were veins of hydrothermal quartz and anhydrite cutting across the units. These indicated that the crater generated a large hydrothermal system later on the rocks. Okay, now you might be wondering, well, what does this crater look like? I can't show you a picture of it because it's buried beneath several hundred meters of sediment, but you can look to the moon. This is the Schrödinger Basin on the lunar surface. It's a little bit larger than Chicxulub, but it is a dead ringer for what Chicxulub would have looked like. The central uplift as the crater was forming collapsed outward to form this wonderful peak ring that you see here, and the walls of the transient crater collapsed outward to form the outermost crater rim that you also see here. So Schrödinger is what Chicxulub looked like. Okay, now I need to introduce another concept to you before I introduce the impact origin of life hypothesis. At about the same time we were searching for Chicxulub, Tim Swindle and I at the University of Arizona were also beginning an investigation of the collisional evolution of the solar system. That included impact melt samples from the asteroid belt in the form of meteorites that had fallen to Earth. It also included many samples from the moon, in part trying to confirm evidence that our predecessors in the Apollo program, people like Jerry Wasserberg and Grenville Turner, had deduced many decades before. Based on analyses of Apollo samples, it had been inferred that very early in solar system history, the moon was severely bombarded. And so I've plotted that schematically here in this diagram. The y-axis is the flux of impacting objects. The x-axis is time from 4.5 billion years ago to today. And so initially the impact rate was very high. It declined over a rate that we still debate. But within the first 600 to 700 million years, there appears to have been a rather high level of impact cratering. As I said a moment ago, we don't really, we still debate the magnitude and duration of that bombardment, but it was nonetheless high early in solar system history. Now, that was very interesting to astrobiologists who noted that that bombardment seems to have ceased immediately before the earliest isotopic evidence of life on our planet about 3.8 billion years ago. Now, the lunar impact record implies there was a heavy bombardment of the Hadean Earth. And calculations by Kevin Zonley and Norm Sleep indicated that the largest of those basin-sized impact events would have vaporized any surface water on the Earth making surface conditions completely untenable for life. So that posed a problem for the origin of life at the surface. So, but based on those observations of hydrothermal alteration in the Chicxulub rocks, I proposed a slightly modified hypothesis, an impact origin of life hypothesis, that argued that that same bombardment created vast subsurface impact-generated hydrothermal systems that were potential crucibles for prebiotic chemistry and suitable habitats for the early evolution of life. Okay, and at about the same time, the biology community was making huge advances using new techniques to study ribosomal RNA, completely redrawing the kingdoms of life, which you see depicted here in a diagram that Jeff Farmer produced. And importantly, this new understanding of life was rooted in a thermophilic community of organisms. That is, organisms that would have existed and thrived in hydrothermal systems, which was completely consistent with the impact origin of life. Okay, so we have this notion that the early Earth was bombarded, and you can see that in this little video that Simone Marchi made a few years ago, depicting the huge number of impact craters that were being produced on the lunar surface. Tens of thousands of hydrothermal systems would have been produced, including hydrothermal systems beneath craters, 6,000 craters ranging in size from Chicxulub to about 5,000 kilometers in diameter. So these impact-generated hydrothermal systems were pervasive. Okay, so I have to say that over the last 20 years, we have been testing this hypothesis just as hard as we can. I did a little count here in the production of this slide. We've now published 31 papers that have tested this impact origin of life hypothesis in different ways. We've conducted petrological, geochemical, and isotopic studies of those hydrothermal systems. We have produced thermal evolution models of those systems. We have produced chemical evolution of those systems, not only on the Hadean Earth, but on Mars. We have tried to evaluate better the magnitude and duration of that bombardment to better understand the cadence of the hydrothermal system production. We've tried to further evaluate the consequences, the thermal consequences of those impact events on the Hadean Earth. We've actually even started looking for samples of the Hadean Earth on such places as the moon, because some of the largest of these impact events would have blasted fragments of the Earth's crust up onto the lunar surface. And we think actually we may have detected a fragment of Hadean Earth granite in an Apollo 14 sample. Okay, so that brought us to this IODP, ICDP Expedition 364 to the Chicxulub impact crater. It's important to understand that Chicxulub is the largest, best preserved impact basin on Earth. So it is our best proxy of Hadean Earth impact craters, and thus our best avenue for testing concepts or ideas or processes associated with that impact origin of life hypothesis. Listed here are some of the key objectives of this expedition. One was to test models of peak ring formation. Another was to test models of impact-generated hydrothermal activity. Another was to evaluate the habitability of that hydrothermal system, and I'll address both of those today. Fourth, to evaluate the recovery of life in a sterile zone. And five, to fine-tune models of the climatic effects of the impact event on Earth. Okay, so let's dig into this expedition in a little more detail. This is a cross-section of the Chicxulub crater as modeled prior to the expedition. This is a model that a former PhD student with me, Oleg Abramov, did as part of his PhD thesis. On the left panel, you see contours of the temperatures in the impact crater or beneath the floor of the impact crater after impact event. And these are contoured from 25 degrees near the surface to 1200 degrees around the impact melt sheet. On the right side of the diagram, our flow lines indicate where water and steam was being produced and flowing. And as you can see, the most intense hydrothermal activity was in the peak ring of the crater. And so the IODP-ICDP borehole was actually sited on the outer flanks of that peak ring. And you can see that indicated there with the site M0077A borehole location. So the first question we were asking ourselves when the core came up out of the water was, do we see hydrothermal alteration in the core? And their answer was very quickly yes. So here are 5 views of 5 different sections of the core. The core is about 83 millimeters wide, which you can see indicated across the bottom of one of the core sections. And in the first 3 panels, I've pointed out hydrothermal channels that cut across the impact breccias that we drilled through. Those are all swavites, if you're familiar with that term. And you can see a green channel in the first panel, and you'll see these bright orange panels cutting through to other sections of the core. We also see in the 4th panel a large number of epidote and quartz veins. We see a dramatic alteration of some of the feldspar in some parts of the core. And in other parts of the core, what you see in the 5th section, we actually see quartz was dissolved right out of the granite. And I should further explain that this granite is the uplifted crust of the Earth in the peak ring that was covered by the impact melt and swavite that you see in the first 3 panels. Okay. Now, if you look at that material microscopically, this is just kind of an array of the different features that you see. We see the precipitation of a large number of high temperature and low temperature hydrothermal minerals. These minerals occupy pockets, they occupy veins, and so forth. And I'm going to actually walk you through a small number of examples of these hydrothermal features. Okay, so let's start with high temperature alteration features. This is a backscatter electron view of one of the granites in the peak ring. And the granite is cross-cut by a vein of K feldspar and albite, which is a relatively high temperature feature seen in alkaline or potassium metasomatism rocks. This is seen in granites, for example, or around granites that are intruded in beneath volcanic complexes. So this is a feature for which we have some petrologic experience in other sites. We also see calcium, sodium, and potassium metasomatism throughout the core, including the impact melt rocks shown here and in the overlying swavites. We see metasomatic fronts moving through the impact melt rocks. Sometimes we see that moving through just as a holistic front moving through the rock. We also see where the metasomatism will take advantage of fractures in the rock, and there's 2 examples of that shown here. Within the same rocks, we actually see cases where shocked quartz entrained within the impact melt was dissolved by these high temperature hydrothermal fluids. And in fact, there's just a little relic of some of that shocked quartz sitting in a void just below the number 85.1, which is the sample number. Once the quartz was dissolved and there was an open void, hydrothermal fluids then filled that empty space with calcite. And so this particular thin section has both high temperature and lower temperature hydrothermal products. This is a vesicle that's been filled by hydrothermal minerals in the same impact melt rock. Here, that vesicle is filled with barite and also filled with smectite group clays. We see 2 different types of clay alteration throughout these rocks. At lower temperatures, we see vugs and open fractures filled with minerals like zeolites. So here in the upper left, we see the zeolite dockyardite, which is that bright orange mineral, and another zeolite called analcime, which is that transparent crystal that you see there, filling in the voids. And then there's a backscattered electron view of the very same minerals growing into a cavity on the wall of potassium feldspar. And I will point out here, because it's important, that there's also some pyrite growing with those zeolites. These are lower temperature minerals that grow at temperatures below 200 degrees. Alteration, I might add, is very pervasive. Here is some impact melt fragments in the swavite at the top of the core that I've been showing you, and the glass is completely replaced by the smectite group minerals, saponite and montmorillonite. In fact, we've not found a single sliver of glass preserved in these rocks yet. Okay, this is a range chart that compiles, and I should say that Martin Schmieder compiled this range chart for the team. This illustrates all of the higher temperature minerals on the far left with the lower temperature minerals as you swing to the right of this diagram, from the top of the core with the swavites to the bottom of the core, which is composed of those fractured granites that I've been described. And so again, one of the points I want to make is we see hydrothermal alteration throughout the core. We see both high temperature mineralization, and we see that higher temperature mineralization overprinted by lower temperature mineralization. Okay, so the next question you might ask is, what is the duration of that hydrothermal activity? And the first thing that we can do is we can turn to that model that Oleg Abramov did for us prior to drilling. And so here is that hydrothermal system about 4,000 years after impact. Here is it after 20,000 years, after 200,000 years, and after 2 million years. So based on Oleg's calculations, this hydrothermal system should have persisted from about 1.5 million years to 2.3 million years, depending on the permeability of the fractured rocks beneath the floor of the crater. Now, I want to draw your attention to another feature on that range diagram that I didn't point out initially, and that is this column here circled in red. That is the magnetic properties that were measured by the magnetics part of the expedition team led by Sonia Tiku. And you'll see that some samples have reverse polarity, which is exactly what you would expect for the KT boundary impact rocks that were produced during Cron 29R, or reverse. But you'll see there also are a few locations along the core where we have black lines or black marks, and that indicates normal polarity. Okay, so that indicates that some of the hydrothermal rocks were crystallizing these magnetic carriers, magnetite for example, long after Cron 29R was over, okay? And so here's a close-up of the magnetic stratigraphy of Cron 29R, 29N, 28R, 28N, and the KT boundary, as you can see there, is within 29R. The first time we see normal polarity is approximately 300,000 years after the impact event. The next time we see it above that is about 1.2 million years after impact event. So the normal polarity that was detected in these rocks thus far indicates the hydrothermal system persisted for on the order of 300,000 years to about 1.2 million years. And that is to temperatures of about 100 to 250 degrees when that polarity would have been locked in to the system. The time needed to reach 50 degrees, at which point hydrothermal activity would have ceased, would have exceeded those time scales, and in fact may have exceeded the model estimates in that Abramoff and Kring study that I pointed to earlier. This is ongoing work. A lot of new details are going to be forthcoming from expedition scientist Sonia Tiku and her student Christina Verhagen, so please stay tuned for more exciting results. Okay, now the vents, this hydrothermal system was venting on the floor of the crater, which was submerged by the Gulf of Mexico. And those vents were carrying some of these metalliferous elements into the sea, which were then trapped in sediments that deposited on top of the peak ring, on top of the impact swavites. And one of the key signature elements is manganese. And there's a diagram on the left that shows the concentration of manganese in our samples across the top of the peak ring impact sequence into the post-impact Gulf of Mexico sediments. And based on the biostratigraphy that is matched to those chemical anomalies, we can infer that manganese was vented into the seafloor for a period of 2.1 million years. Okay, so the lifetime of this hydrothermal system was on the order of 2 million years, or perhaps a little bit longer. Now, we're talking about the impact origin of life hypothesis, and so at some point I need to get to this issue of life, and so now let's make that leap. I pointed out that there are pyrite crystallized within the hydrothermal system, and here's a wonderful picture of some of those pyrite framboids within the zeolite's analcene, okay? Sulfide framboids in several regions of the impacts within low temperature and thus biologically compatible mineral assemblages imply sulfate reduction was a viable energy source for microorganisms, okay? And we're gonna zero in on that process, okay? So if that did occur, the first thing those organisms would need to have is a source of sulfate. And so the logical question to ask is, was sulfate available? And the answer is yes. The impact event actually occurred in a carbonate platform sequence with abundant anhydrite. Here is a much younger David Kring, there on the left, holding a large core segment entirely composed of anhydrite that we recovered in a different expedition, an ICDP expedition around 2001 and 2002. And so water coursing through that rock would have picked up, dissolved and picked up some of that sulfate and carried it into the hydrothermal system. In addition, in some of the swavites, we actually find class to those target rocks anhydrite, and those hydrothermal fluids course through those rocks, picking up the anhydrite. And in fact, we know that occurred because we find these hydrothermal anhydrite-filled veins, and there's a couple of pictures of those in thin section view there. And we also find anhydrite precipitating in some of the voids or cavities within the swavite at the top of the system. So we have a source of anhydrite, and we have evidence that the hydrothermal system picked it up and carried it throughout the rock sequence. Now, we also have evidence that sulfate was converted to sulfides because we see abundant sulfides throughout the rock sequence. Here is a couple of panels of some of this sulfide. And I want to draw your attention to the top four, the picture in the top row, because I want to show you isotope analyses of sulfur in these four samples. Near the top of the sequence, just a few meters beneath the top of the few meters below the seafloor of the Chicxulub crater, we have these euhedral grains of pyrite. A few meters deeper, we have these pyrite framboids. A few meters below that, in the third panel, we have an additional population of pyrite framboids. And way at the bottom of the core, deep within the granite, we have these euhedral pyrites. Now, I have to say that the pyrite framboids are very interesting because they have, in other geologic settings, been associated with microbial ecosystems. Okay, so now let's look at the sulfur isotope composition of that pyrite. And this is a little bit of a complicated diagram, and so we'll spend a few minutes on it. The first thing I need to point out is the data are plotted as a function of depth on the vertical axis. And so data on the bottom of the diagram are at greater depths. And then along the horizontal axis, I am plotting the sulfur isotope composition in Del 34 sulfur notation in a per mil levels. Now, the next thing I want to point out is the composition of the source sulfate, the anhydrite that is in the target rock. That is characterized way at the bottom of the diagram in the far right corner as a series of gray data. And the average composition of the target anhydrite in the crater is 18.3 per mil, which I've indicated with a vertical line. Now, the data for the 4 samples of pyrite that I showed you in the preceding chart is depicted in these clusters of colored data points. The euhedral at the base of the core within the granite is in the pink squares. And that shows a fractionation between that sulfate and that sulfide of about 20 per mil. That is the maximum abiotic fractionation that you can have in sulfur. And so it's quite possible that there is nothing biologic associated with the composition of that euhedral pyrite at the very base of the core, deep within the granite. However, if you now go a little bit higher in the core, if you look at the gold data points from one of the swavites, you see that the fractionation in sulfur between the target sulfate and those pyrite framboids ranges from about 24 to 40 parts per mil. That greatly exceeds what you can do with physical fractionation processes. That amount of fractionation requires biological microbial activity. And the fractionation is even greater in the next highest level of swavite, which you see there in green dots, which is also fractionation captured in those pyrite framboids. If you go to the top of the sequence, where we have a slightly euhedral pyrite, but also within swavite, we have slightly more modest amounts of fractionation, but again, it exceeds the amount of fractionation that one would expect by physical processes alone. And so in 3 samples, in 3 parts of the impact swavite polymic breccias at the top of the sequence, we have evidence of microbial activity. Okay, now, you might ask yourself, does that make sense? Do these minerals, pyrite, which are entrained with analcime and daciardite, 2 zeolites, make sense? Could microbial organisms exist at the temperatures at which they persisted? Okay, so we go to geologic analogies or analogs. So in natural hydrothermal environments, analcime and heulandite, which are 2 of the zeolites, are generally produced at temperatures between 25 degrees and 100 degrees Celsius. Heulandite may follow analcime precipitation as temperatures fall below 100 and 120 degrees Celsius. In fact, at Yellowstone, heulandite was observed at hydrothermal temperatures of 40 and 80 degrees C at depths of 17 and 30 meters respectively. And those depths, by the way, are very comparable to the depths that we're talking about in Chicxulub swavites. Pyrite framboids in association with heulandite, analcime, and calcite have precipitated from submarine vents with fluid temperatures of 87 degrees. That's been observed in a modern setting. And now returning to our samples, I'll point out that our pyrite framboids in one of our samples is associated with calcite. And clumped isotope analyses of calcite, this is another method I can't get into in this talk, but that method which has been applied to calcite deposited immediately on top of the breccias with pyrite rhamboids, record hydrothermal temperatures of 70 degrees. That's another expedition report led by Tim Bralauer at Penn State, and that's published in HU Advances about 4 weeks ago. Okay. You might also ask the question, well, you're arguing for sulfate-reducing thermophiles. Do such things exist? And do they exist at those temperatures? And the answer is yes. These things have been documented for about 30 years, actually longer than that. Here are some examples, a small subset of the examples that are available in the literature. So here, for example, in the top bullet, you'll see 2 examples were isolated for hydrothermal vents in the Gulf of California's Guaymas Basin, which is just off the coast of Sonora if you're not familiar with the basin. And their sulfate reduction peaked between 60 and 90 degrees Celsius. And there are a couple of other examples. Okay, and so this is the picture that the expedition has drawn or crafted for us. We have a central melt sheet, which is heating water in the subsurface and driving this hydrothermal system. Those hot hydrothermal fluids are rising at the edge of the central melt sheet and venting at the peak ring that we drilled into. Most of the water in this system is groundwater, and I have to acknowledge that we don't have evidence for that yet in this particular core, but in a previous ICDP core analyses that we did, isotope analyses that we did of that core indicated the water was dominated by groundwater as opposed to seawater. Also in the thermal evolution modeling that Oleg Abramov did with me, that indicated that most of the water in the system was groundwater as opposed to seawater. But in both cases, we have evidence of small contributions of seawater. And so you can see diagrammatically or schematically have illustrated that there could have been some drawdown of seawater into the system producing chemical mixing zones. And as I indicated in the previous charts, the last half dozen charts, this hydrothermal system also hosted microbes, both bacteria or potentially bacteria and archaea. Both of those domains contain sulfate reducing thermophilic members. Here actually is a view of one of these sections of rocks. So this is again a picture of one of these core sections. It's about 25 centimeter core length, about 83 millimeters wide. And then here is one of these, you can see pictured here, one of these pockets, brilliantly orange because it hosts dockyardite and the other zeolite analcine. And within those populations of zeolites are these pyrite rhamboids, one of which we analyzed and showed you in previous charts. Okay, so in conclusions, in the last couple of minutes here, I want to draw the conclusions by providing answers to some pre-drilling questions. And the first of these is the peak ring deformed, that is it sheared and shattered and thus permeable to hydrothermal fluids? And the answer is yes. There's abundant shearing, and you can get more details about that in a paper by Ulrich Riller, published in Nature in 2018. That shearing is similar to that inferred from geologic mapping of Schrodinger based on the moon. Remember that perfect analog from Chicxulub that I showed you? It's also similar to the permeability that we modeled in that thermal evolution model that I pointed to previously. I have to say that the team is still working to quantify the permeability using petrophysics and other techniques, but that will be appearing hopefully later this year. Second question, is the peak ring hydrothermally altered? And the answer is yes. I've shown you abundant evidence of that, which confirms the impact generated system was widespread across the Chicxulub impact basin. Was the hydrothermal system hot? greater than 300 degrees C. Yes, both calcium, sodium, and potassium metasomatism and quartz dissolution indicate temperatures of 300 to 400 degrees C. Was the system long-lived? And the answer is yes. The high temperatures indicate that cooling would have taken at least 2 million years, and also paleomagnetic clock and manganese contamination of post-impact submarine sediments imply a similar timescale. When the system cooled, did it host thermophilic and hypothermophilic organisms? Clearly, there was sufficient habitat for organisms. The hydrothermal system created this wonderful network of niches perfect for microbial ecosystems. And we now have, published this month, sulfur isotopic compositions of pyrite framboids indicative of sulfate-reducing thermophiles in those niches. And if that model that Oleg and I put together years ago is correct, conditions suitable for that type of life may have existed in this part of the peak ring for order 10 to the 4, 10 to the 5 years. The two final questions I want to address: does the work support the impact origin of life hypothesis? And yes, for all of the reasons given above. Studies of Chicxulub have thus demonstrated that large peak ring and multi-ring basins have porous, permeable subsurface environments, that such impact craters host vast subsurface hydrothermal systems, and that those systems can host microbial ecosystems. And then finally, does the model have broader implications? And the answer is yes. Impact cratering is a fundamentally important heat engine in emerging planetary systems. Impact-generated hydrothermal systems are possible wherever water exists in a crust, and the model is therefore transferable to an early Mars. It's been postulated by many other investigators in the past, and any exoplanetary system with similar conditions. With that, I want to thank you for your attention, and I will take any questions.
Thank you, David. If there are any questions, you can post them in the chat box and we can read them out, or you can unmute yourself and ask those questions. So we have our first question. David, would you like to read it, or should I read it from the chat box?
Please read it if you would.
Okay, so we have a question from Jen. Have any fluid inclusions been identified in these samples?
Fluid inclusion studies were done in the previous ICDP core samples, and those data are very important to the story because it actually indicates that these fluids actually were also carrying hydrocarbons, which may have provided the electron donors needed for the thermophiles to reduce sulfate to sulfides. But I have to, and we have seen fluid inclusions in these new core samples, but we have not yet published any of those results. So that's another one of these results that you'll just have to be a little bit more patient before we are published. I have to say that we have a draft manuscript, but the pandemic really put a hold on that because just a little bit of more analytical or laboratory work was needed before we submitted that. But that should be forthcoming as soon as conditions improve.
Great. Here is another question. What is it you're looking for as an isotopic evidence of life?
Well, in this particular, in the case that I just outlined now, we were using sulfur isotopes as a measure of biological mitigated sulfate reduction. As I indicated earlier, you can fractionate sulfur isotopes using physical processes, but the magnitude of that is 20 per mil or less. Whereas if you have microbial organisms in the fractionation loop, you actually can get fractionation considerably larger than that. And so that is thus far the isotopic signature of life that we have utilized so far. But there are many others. There's a number of investigations that are ongoing Again, I think what you see here is just the tip of the iceberg, so to speak. The core, to put it another way, the core is truly extraordinary. It greatly exceeds all of our pre-drilling expectations. And so there is going to be a large number of very exciting astrobiology related results forthcoming.
That's great. Thank you. Here is another question from Paul regarding how widespread hydrothermal activity is as a function of the radius. Can you talk to what the major gaps are and how they might be filled?
Well, based on both the modeling that we have done and based on the samples that we have from this borehole project and other borehole projects, we have deduced that hydrothermal activity occurs across the entire diameter of complex craters, whether they be central peak complex craters or peak ring craters like you see here. Now, the hydrothermal system may not persist in all portions of the craters at all times. That is, as the impact melt sheet in the center of the crater cools, the outer portions of the crater are going to cool first, and hydrothermal activity there is going to cease first. The location where hydrothermal activity is going to persist the longest is going to be in the peak ring at the margins of the central melt sheet and above the impact melt sheet. Now, something that may not be self-evident is that large hydrothermal circulation in the center of the crater will not occur until the melt sheet cools and sufficiently to sufficiently low temperatures to solidify, because it needs to be able to fracture before hydrothermal fluids can actually permeate it. So the hydrothermal activity is going to be longest both in that peak ring and above the central melt sheet.
Great. Do we have any more questions from the audience? Oh, here is another one. Are any future drilling expeditions planned, and what would be the objectives?
One thing that, this is a question that has been asked before, not only by scientists in the community, but by funding agencies. And so I've answered this question in the following way when speaking with NSF, the International Continental Scientific Drilling Program, and the International Ocean Discovery Program. Chicxulub is an immense structure. It's roughly 180 kilometers in diameter, and it has a lot of different geologic domains and a lot of different hydrologic domains and a lot of different biologic domains. And there is no way that a single borehole can capture all of that evidence. And so I've mapped out that to really capture what the evidence within the Chicxulub crater, you need to think of this structure as a 6 to 8 borehole target. And so we have now drilled 2 scientific boreholes into this structure. This ICDP borehole in 2001 and 2002, this IODP ICDP borehole in 2016. And so we really need to make plans for another 4 to 6 boreholes. And the question is, well, what might they uncover? Well, one thing that we really would like to do, but it will require a much deeper borehole, is to actually drill into the central melt sheet all the way through the central melt sheet into the floor beneath that melt sheet. We want to actually confirm our estimates of the thickness of that melt sheet. We want to determine whether that melt sheet differentiated like the Sudbury melt sheet in Ontario. We want to know whether some of the denser minerals, like sulfides, settled out of that melt sheet to the floor of the melt sheet as we see at Sudbury. We want to determine whether that melt sheet thermally eroded the floor of the crater. And of course, we want to see what type of hydrothermal activity actually existed within the center of the crater, and whether that too hosted microbial ecosystem. So that's just one example of the type of and scope of science that a borehole in a different location might provide.
Great, thank you. And here is a question relevant to the previous one. What was considered in the choice of the drilling location? Why was these particular locations chosen?
Well, it was driven in part by those 5 science questions, those 5 objectives that I pointed to earlier in the presentation. We had, and maybe it's worthwhile to actually say how this type of expedition, the path towards this type of drilling. So one looks at the structure, one looks at some of the scientific questions that can be deduced. One tries to identify different locations within the crater that these could be addressed. And so we start the process looking at several different borehole locations. Then we ask, well, what are the highest priority scientific questions? That is, which borehole gives us the biggest bang for the buck, if you will. We then have a meeting. The first meeting for this project actually occurred in 2006 in Potsdam, Germany, where we discussed all of this. We discussed the different borehole location possibilities. We had to determine whether we had sufficient seismic data to guide the drilling effort, or if additional seismic data had to be collected before the borehole site was finalized. And then, of course, we had to go through a large number of reviews to actually raise the funds, deal with issues such as the hazards that might occur with drilling into this particular location, getting the licenses and the permits for drilling in these different locations. All of that took about 10 years to do. In this particular case, as I said, the highest priorities were scientific priorities that we identified were to determine or test models of peak ring formation, test our models of impact-generated hydrothermal activity, test the capacity of that system to host organisms, to determine how life may have recovered within ground zero, the crater at ground zero, if you will, and to determine better measures of the post-impact climatic effects of the impact event.
Great. Here is another question from Paul, not a geology question. What is the water depth?
Oh, the water depth at the time of drilling, where we drilled, was only about 17 meters. And okay, so that actually required us to use this oil drilling platform. That's what we used. This is an oil drilling platform that was actually leased from a company near New Orleans. And this platform was floated around the margins of the Gulf of Mexico to the northern edge of the Yucatan Peninsula and tethered, and drilling then commenced. The water depth is so shallow here that we could not use the normal large drilling ships that IODP has access to. So the United States has a very large drilling ship. The Japanese have another very large, in fact, larger drilling ship that IODP uses. Here, we had to use a special platform, and these types of special platform IODP expeditions are funded through the European branch of IODP. Now, I should then add, since we're talking about water depths, that after the impact event, the estimated water depth above this portion of the peak ring was 600 meters.
That's great. That's awesome. Thank you. Are there any more questions from the audience? All right, we are at the end of the hour. So if there are no more questions, let's thank our speaker one more time. Thank you so much for such an excellent talk.
My pleasure.
And I'll hopefully see you all next week. Thank you.